Hello, everybody. This is my quasi-lab report for the day. It is not actually December 3rd. That's just for my defense. Today is November 30th. I have Autumn sitting in with me to be my live guinea pig to listen to it. So, without further ado, I will get going. This is a presentation of my proposal defense for my thesis work. It's basically UAV-based measurements of the urban forest. I'd like to thank Dr. Pingo, Dr. Lowe, and Dr. Shagnon for helping me with this, and also Dr. Allred. So, basically, an urban forest is simply put all the trees within an urban space. It is a very dynamic system, which means things change a lot in it. For the average roadside tree, the half-life is only 13 to 20 years. So in DeKalb, that means alone, every 5 years, about 2,200 trees will be either removed or replanted. This makes keeping a good count of them very difficult. But to manage them, you need to have very good inventories of this tree database. So these need to be current, they need to be comprehensive, and there's multiple types of factors that are generally needed. Usually like the type, number, and distribution of the trees with their health, size, and age. This is traditionally done through surveys. The most common method is the traditional ground-based field survey, which means somebody goes out there and actually measures things by hand. This is very time and labor intensive, and because it is so time and labor intensive, it gives you a very low temporal resolution, which means they only do it very infrequently. A newer version, they've actually started using remote sensing techniques, and the primary one right now is airborne laser scanning. This has the problem of having very high monetary costs because you have to contract out to a company to do it, and it also, because of that high cost factor, it has a low temporal resolution. So what I'm proposing is using unmanned aerial vehicles to combine the best possible techniques for doing this. The UAVs have come a long way recently. There is now a lot of good quality commercial grade units out there with very high resolution camera capabilities. They are very easy to operate. They can be used in areas of multiple sizes. They can be rapidly deployed whenever you need them. And best of all, they take these really good images that can be processed to generate the tree data. And the two methods that we're going to be talking about are structure from motion, which is a type of photogrammetry. We'll actually get into these a little bit later. My basic research question to top this all off is, are UAV-based urban forest tree height and trunk diameter estimates more accurate compared to the ALS, the airborne laser scanning, and the GFS, the ground-based field surveys? To do this, there's four topics we're going to look at. The first one is the quality, the time of collection, the leaf off versus leaf on collection. There's a couple different factors in this, but I have two thoughts on this. One, I think that the leaf on state will provide better measurements for the tree height, but I do think the leaf off condition will actually provide better measurements for the tree diameter. The second topic of consideration is a fusion process with these data sets. Because I'm going to have these two separate data sets, I feel that there is going to be some value by taking these data sets and actually merging them together. I think that should improve our tree height measurements, but I still think the leaf off situation will give us our best trunk diameter measurement. The third topic is neighborhood. There's different types of neighborhoods, and they each have their own characteristics within the neighborhood, usually dealing with the age, type, size of trees. I think for the new method I'm proposing, it will actually function better in newer neighborhoods due to the fact that trees are usually less mature, there's less crowding, they're a little more open. So I think that that'll actually have a beneficial effect on it. And then automation. Right now with the technique, I will be going through and manually measuring most of this data, but I propose there is a way to build an algorithm to do this automatically. With that algorithm, I think it'll be faster than a person can do manually, but I think the quality of measurements may be better doing it manually. 5 minutes in already. Okay, so a little bit of background. An urban forest. Basically, like I said, it is all the trees within the urban structure, but the urban forest tends to differ from what you would consider a natural forest system. There is a large mix of different styles, types of trees, ages of trees, placements and arrangements of trees that you're not normally found in a natural setting. And that's because the species are selected for their ornamental purpose. People like to enjoy what their trees look like, as opposed to a natural evolutionary process of forest progression. Urban forest management is something that most governments need to take a look at. We have the problems with, Dutch elm disease or ash borer beetles, so they need to know what is there. Like I said before, these are performed by hand usually, but it does allow the trees to be sampled individually. Classic way of doing this is taking a big pole and holding it up next to the tree, or using what's called hypsometry, where you measure the angle to the top of the tree and the distance from the tree so you can extract the height. Then also you want to get the trunk diameter, which is typically done by taking a tape measure and just literally measuring it. That is one thing that can actually allow you, there is this thing called telemetry, which allows you to extrapolate from that tree diameter at breast height, which is 1.3 meters above the ground, and extrapolate what the height is going to be. That's not one of the things we're really dealing with here, but it is something to know. And when you're doing it in the field, you can also gather other data about it that you can't get from remote sensing techniques. But as we've said before, this requires a lot of time and labor. ALS, or airborne laser scanning, it can rapidly scan large amounts of area. It's being taken by an aircraft, either a plane or a helicopter, so you can get large areas very, very rapidly. And it's also called LiDAR, which is light detection and ranging, which is a method where packets of lasers are beamed out from a sensor, and then the reflections are coming back, and you take the time it takes and the angle that they do to find a three-dimensional spot. It has a very high spatial accuracy. Most testing finds between 1 and 6 centimeters is very good for your vertical accuracy on most of these. And the points that give back allow you to build a three-dimensional representation called a point cloud. There's all these individual points where the lasers are bouncing back. You can build a three-dimensional space out of that. An additional advantage to airborne laser scanning is that it can actually penetrate through some of your canopy cover, which improves your detection of the ground, which makes your tree estimation a little bit better. Some problems that we do have with ALS is that there can be underestimates of the height because of lower limit threshold. That means there has to be enough energy in the reflection coming back for the units to actually classify it as a reflection. So you lose a lot of data that way. And the other is, due to things like lower limit and just reflection, you get very low point densities. Typical ones can be between 10 and 12 points per square meter, which is not a lot. And when you're dealing with tree canopies, they tend to change a lot in that space. And the most prohibitive is the high cost of generation. The data set that I'm using for reference here, the DeKalb County survey taken in 2009, actually cost $179,000 to do. And so they do not have any plans to redo that anytime soon, and you can't really blame them. So what I'm suggesting is we use UAVs. They only take a single or a small crew to run. The flight parameters can be adjusted to suit each individual situation. You can change things on the fly. If you do something you don't like, you can immediately change it. You have things like the height, overlap, your exposure, all these can be adjusted. Flights can be repeated, and the imagery is getting better each and every generation. It's very high resolution imagery right now. Large amounts of this can be generated quickly, and it can be either still frame or video. Now, to take that imagery, what we can do is use a process called photogrammetry, which is a process where two-dimensional images are used to create three-dimensional data. This can capture a lot of spatial detail, and to process it, you need to know a couple things, basically flight height, focal length, your scale that you're imaging. What it does is you scan the images for identifiable points, and then you just track the changes and use some processing to extract data from these. This has been used successfully in quite a few vegetative studies. What I'm going to use is something called structure from motion, SFM. This is basically an advanced form of photogrammetry. It developed out of basically computer vision learning. Trying to teach computers how to do things, they found that you could actually use this to sequence large blocks of images together. So it actually takes an entire sequence of images and it scans for all these details through it and extracts your points from that way. When you get these points out, they can be processed with the same tools that we use now to process LiDAR. So there is already a suite of available tools to use, and they tend to have much higher point densities. The preliminary data that I've used, I'm averaging over 1,000 points per meter squared, which is orders of magnitude larger than you're getting from standard LiDAR. We're going to have to... Okay, we're back. There was a little bit of jump there. We had some interruptions, then Autumn had to go to class, and we ran out of time there. So I am back now. We were talking about the structure from motion portion of the UAV scenario. Right now, it's increasingly being used for tree height estimation. It's being applied in multiple natural forest and agricultural settings currently, but the usage in the urban forest has been limited. There are some limitations that you must account for when using structure from motion. The primary one is the image quality and coverage, and the quality can be influenced by the camera lens, the pixel depth and resolution. The coverage is the image overlap. You really want to have enough there so you can track points in the images in multiple frames for the best representation. The image that the height is actually taking above ground level and the angle that the cameras are working at. And the environmental factors, basically illumination and the relative angle of the sun, shadowing effect. There have been several studies that have used structure from motion already. I put a table in here that had a lot of different tests run on them. Lots of the comparisons are between UAV versus ground field-based measurements, ground-based field measurements, and UAV versus ALS. The results that have been gotten in most of the other studies find the root mean squared from ground to UAV. It's ranged from a third of a meter up to about 3 meters, depending on the forest type. And ALS to UAV, they found between 1 and 3 meters also is pretty much the range that the root mean square errors have come through as. For this study, we're going to be using here in DeKalb. The sample set region is one that was identified by Dustin Bergman in his thesis work. There are 2 main sampling areas. We have the historic area and a new development area. These zones are chosen because there is a wide range of conditions within these. There are 2 primary differences. We'll talk about those in a second. And the sample will only be limited to the public trees on right-of-ways and in parks. So the historic area, these are older areas. There's one of Elwood and Huntley Park. There's about 710 trees in this area. These are larger, more established trees. The spacing is irregular through loss and replacement, and there is a very heterogeneous mix of species. There's several different species all mixed through that area. The second study area is the new development area. These are younger neighborhoods. They're still developing with growing trees. The areas are the Knolls and Kensington Point. This study section has 325 trees in it. They're newer growing trees. They tend to have more regular spacing, and there is a more homogeneous mix of the trees there. Okay, what we're going to need to do is deal with our data. These are our data sets. The first one is the ALS data set, the Airborne Laser Scanning Set. It was acquired in 2009, was professionally acquired by the Sanborn Map Company. The flight altitude of it was 1,400 meters. Average point spacing on the ground for their returns was 1.2 meter, which is not a lot. So there's a lot of gaps in coverage. So it can make it kind of hard to really get a good estimation of the trees with this one. For this, Sanborn reported their vertical accuracy about 6 centimeters, and their horizontal accuracy was around 1 meter. The data was georeferenced to the Illinois State Plain East, and this is the layer that we will use to reference all additional layers. The second is the ground-based field sample data set. This is one done by Dustin Bergman. This sample set has 1,035 trees in it, and it was sampled during the leaf-on conditions. This is probably the best to maximize the actual tree height estimation for me, but for Dustin's survey, he measured the tree heights using a laser ACE hypsometer, and he manually measured the trunk diameters. A subsample of 10 trees was measured using a total station, and it found that it had about a 0.7 meter root mean squared for all the hypsometric samples. The data sets that will be generated with the UAV will be 4 different sets. There will be manual sets, which will have the 2 leaf sample conditions. Those will be the leaf on and leaf off sample conditions. And then there will be a third set, which will be the merge point cloud, where I'm taking the 2 sets and trying to align them so you get a full body representation of the tree. We will also have the result of the algorithm that I should be developing. This should be it's going to be a custom designed algorithm. Okay, so with this, there are some flight parameters. I'm using a DJI Mavic Pro. My flight height is going to be 200 meters. That's from launch point above ground level. The camera angle I use is a 70-degree oblique, and I use an 80% image overlap. For processing, I've been running on a Dell PowerEdge R720 server. It's running 2 Intel E5 2670 processors, and I'm running about 118 gigabytes of RAM on this. For cloud generation, the first step is we're using the Pix 4D Pro Mapper software. It is a stretch for motion software program that we have through various different sampling methods. We found this to be the best one for us. The software will produce an image mosaic so we can properly align and georeference all of our imagery for it. And we'll be generating the point clouds out of that. The images from our flights will be used to process this using stretch for motion. And the points are put out in a .las file, which is the exact same file that you get LiDAR data in. Okay, here are a sample of some of the items that we've actually processed so far. These are actually point clouds. They look very, very good. When you get into them, there's a lot of really good data. These are leaf-on conditions. Now, once we have those point clouds, we will need to manually extract our data. This is being done in Cloud Compare, which is an open source, open software program. It's specifically designed for point cloud manipulation and analysis. The trees will be manually measured by me for this first section. I will go in and manually measure the tree height and the tree trunk diameter. Over on the right side, you actually see this is a result from one of the Pix 4D samples. For one of my sections, it's giving me an average density per meter around 1,200 points, which is very good. It gives very good results on it. And the whole section there, as you can see, is 3.6 billion points, which gives us a real good visual image. The processing for this took about 5 days for that stage. Then what I'm going to do is try to build an algorithm to replicate this. We'll need to generate the ground level for each of these samples. Then it must be able to locate each tree within it, identify the highest point of the crown, measure that height, and then identify the trunk within the tree structure and measure the diameter at breast height. This is just a sample of one of the processes I go through. These are point clouds. I just go in, I find the top and bottom, measure it. And the other one, you sort of try to identify the trunk within the structure and manually measure that across. Now for the data analysis, there's going to be 2 types of analysis that will be run. One is just the statistical analysis of the data itself. I'll be running regression analysis and root mean squared error comparisons. I plan to take the UAV manual extracted data points and compare those to the ground-based field samples. I'll also compare them to the aerial laser scans. And then I will compare the data with the algorithm-derived values also. The second thing I plan to do is look at the temporal component of the processing, because one of the ideas is to try and make this a time-saving option for whoever uses it. So I will want to go ahead and compare, if it's available, the time of collection for UAV versus aerial. Also, the UAV based on a ground-based field sample, how much time it takes between those, and then the actual just data generation. How much time it takes to manually do generation versus algorithm. Have an idea of what that will be, but we'll have to see. So with this analysis, besides our main questions, we'll get a feeling of what difference is there between the data from the different collection methods, what's the difference in time required, what is the time for processing, which is always a major concern, and what is the difference in labor requirements. So that brings us to the basic conclusions that public resources monitoring is a very important thing, and one of these aspects is the urban forest inventory. But in order to monitor the urban forest, you need to have a method that is cost efficient and repeatable on demand so you can get that temporal resolution very low. I think that this UAV method will be a reasonable method for monitoring and inventorying tree data. And I think the regression analysis and root mean squared values will show that there are differences between previous methods and the new UAV-based method. And I think this will allow us to present a functional surveying, processing, and analysis method. This is the timeline I have for it. Right now, I'm looking to finally defend the thesis. After this, we'll start just going out in the field, updating some of the tree surveys that from Dustin's selection, making sure that trees are there and nothing's been changed. Then I will start the manual data extraction process, which I'm estimating will take probably 200 to 250 hours just to really get the feel of it and get it done really right. I need to start running some more comparisons, and that's where I should be by the end of the year. Starting the year, we'll continue the extraction, start actually developing the algorithm, and finally get some processing around springtime. Then finish writing the proposal and defend it. So that's where I'm at, everybody. Hopefully this wasn't too bad for you. I sort of ran over. Yeah. What am I at, about 25 minutes? Yeah, around about 10 minutes over. I would appreciate any feedback anybody has on this. I'm trying to cut it down. Believe me, this is actually a lot shorter than my first draft of this was. So look forward to hearing from everybody. Talk to you later.